Off by thanking everybody for joining us today on our Intro to Results Evaluation with Creo Simulate 2.0. For those of you who haven't been on our presentation before, please note that you are in listen-only mode, so please enter any questions that you have into the box, and we'll get to as many as possible following the presentation by Sukumar. My name is Jason Hardebeck. I'm the National Support Manager for the PTC Solutions Group, and Sukumar is the Engineering Manager. Real quick agenda. I'm going to start off with a couple-minute introduction to BWIR for those of you new to the presentation. We'll pass it over to Sukumar. He'll do a live demonstration, and then we'll wrap it up with a couple of questions, and we'll get to all your couple poll questions as well. Barry-Wehmiller National Resources, we're the Engineering, IT, and Manufacturing Solutions Group of Barry-Wehmiller, Inc. Corporation that's been in business for going on 130 years and approaching $2 billion in revenue. We work with companies to help them get better products to market faster through a variety of areas by improving people, process, and tools from anything from CAD, CAM, PLM, in the engineering services, ERP. This slide kind of shows some of the areas we help people. We have more than 1,000 consultants all across the globe who help us work with our customers to achieve their goals and reach their initiatives. We are U.S.-based, but we do have presence across the globe. This slide goes into a little bit more depth of each of our different areas we work with customers in. The one we're focusing on today is, of course, product solutions. We're a platinum-level PTC partner, and we cover their entire product suite of training services and solutions. We also do offer engineering solutions, everything from product design, machine design. We do a lot with electrical controls, PCB boards. And then we have our enterprise solution group that focuses more on things like ERP, enterprise asset management, customer relationship management, and just about anything else involved in the product development process. As I mentioned, we are one of only 3 platinum-level PTC partners. We were the fastest-growing partner in North America last year. We have 8 training centers located across the United States and also provide training on-site, local area training. We do mentoring. We do customized training. We can do it virtually, just pretty much anything to help you meet your training needs. All of our technical staff's great. You'll see from Sukumar today, but they average over 15 years experience using these products both in classroom and real-world environments, which you don't find everywhere. This just shows some of the companies we work with. You'll notice some larger companies here, but we work with companies of all sizes. I mean, everybody has the same problems, whether you're a small or large corporation. They're just usually magnified in larger corporations. So we work with both small, medium-sized manufacturers as well as some large manufacturers across all these different areas. I'm going to go ahead and pass the demo over to Sukumar and let him take control and get on to the presentation. Can you take control, Sukumar?
Yes, I can show my screen.
You can see your screen.
All right, thanks, Jason. I hope you guys doing well. I know it's lunchtime and you guys hungry, so I'm going to keep it interesting. The things that we're going to talk about today are basically everybody can produce colorful pictures in Simulate, right? You don't need to be an engineer to produce colorful pictures. So garbage in, garbage out, basically. So what we're going to talk about is, one, how do you post-process these results? How do you find information that you're looking at? How do you know if it is good? How do you know what's critical? Okay. We're also going to talk about, manipulating the model, orientation of it, kind of creating results templates so that all your results windows look similar. Maybe you'll have a certain standard established for your reports. How do you achieve that? Creating cross-sections through the model where you cut across and kind of see what's happening inside the model instead of looking at the surface results. You also can query. You can do graphs, minimum, maximum values in terms of dynamic queries. So how do you do the queries in there? How do you print results to different formats? Okay. Now, what is, excuse me. What I'm also going to talk about at the very end, if time permits, is how do you read the results summary file, and how do you approach a simulate problem in terms of, how do you know that you can trust the quality of the solution? Okay, if time permits, we'll cover that. Otherwise, we'll push it up to a next available webinar day. All right. First and foremost, I'm going to talk about annotations. So notice that here within the annotations folder, I have my part. That folder right here shows me it is the name of the analysis. So when you run an analysis and you kind of name it, it basically creates this folder inside there with a bunch of files. Okay. Another thing is, notice there's a file here called RWD. RWD stands for results window definition. RWT stands for results window template. Now most people kind of approach this in this way, right? You go ahead, set your working directory. That's important. You open the part. You get into Simulate. You look at your analysis, right? That's one way of getting in, okay? Now, another way of doing it, I'm going to close this, close off everything. Another way to do the same thing is that you can open the results, simulate results directly without even opening the model. Okay, if somebody can give you a simulate results file, you can just open it directly without having a license of Simulate. So in order for you to run the analysis, you need a license. But in order for you to view and review the results, you don't need a license. Okay, so here I'm going to click on the Simulate Results button, and you can say File Open and open a results window definition, or you can say Insert a results window and create a new results window. So you have two options here. So I'm going to go with the first, and then I'm going to show you how to save it, and then I'm going to show you how to open it. So here's the Insert Results Window definition. So when you do this, you'll see your annotations modal analysis. This is the results window for a modal analysis. So I'm going to open that. Here are a few things that you can do. You can name this window, say mode 1. You can give it a title. Okay. You see that that particular analysis is right here. You can pick different mode shapes here. You have different types of results that you can get. We'll get into that. Right now I'm looking at fringe. I'm looking at a displacement plot, and I say OK and show. Oops. Let's take out the spaces. And there it is. Now here in this results window, notice there are a few other things. See, all your views are right here. These views are also your save view orientations that you have in the model. Okay, so all your save view orientations are here. You can reorient to go back to your previous orientation. See that? I can spin, go back there, zoom in, zoom out, repaint. I'm going to get through this in a second right now. You also notice at the very top you have new results window, open an existing results window, save this, save as a template. You have different export categories that are here, and you can also print. All right. So let's start off with this. So if I go save it, so let me kind of like spin it in a certain orientation, and I go save. I'm going to save it as, say, test. Notice the file type here at the very bottom, it says RWD. So you saved it. Now I'm going to close it. And anybody can just go insert, open, and open that test RWD. See, it saves the orientation too with it. So if people, say for example, somebody in management who doesn't know how to orient or view the result or whatever, right? You can save them so that they can look at it in a certain orientation. You can save it. Now again, once they open, they can definitely spin it around and make all kinds of changes they want to make with it. Okay. So I'm going to say insert a results window, pick the analysis name. So again here I'm going to give it a title. So display, I can look at stress, I can look at displacement, and you see all the different components. Even with respect to stress, you have all your different components. Okay, and say OK. All right. So now you can also go save this as a template. So when you save this as a template, you see that save the units, save the legend values. You see that the legends right here. Save the model orientation, and then you can give it a name and save it. Okay. So when you save this as a template, you can also insert a new results window based on this template so that you don't have to make all these changes every time. Okay, we'll do that at a later point. In the edit, you see you have results window edit. So this button, I click on that, it basically gets me back the results definition window. You can also achieve the same thing by clicking over here. It says edit results definition. So you can say, okay, I'm done looking at the first mode. I'm going to look at my second mode and say, okay. Right? So you can edit. You can also edit the legend value. So if I click on legend value and I can pick this particular number in yellow, I can say I want that to be about 900. So you see that's exactly 900, and then your results window will change accordingly. As of now, this legend is evenly distributed from say 0 to say 1346. You can change those and pick specific colors. So you see legend, I'm going to pick let's say 670. I'm going to say this, I want this to be 750. So you see how your color schemes can change. So you can say anything that's 750 will be in a certain color. So you can edit that legend. All right. You also have view where you can repaint, spin, zoom, orient. You can have shading on and off. You have these details. You can also insert different results windows from template or create new ones. Info, you have more in terms of the query. Format is where you can format the results window and the legend. So if I go format the result window, I can say background color is black, background color is blue, or Creo. Right? I don't want to see the title, so you can get rid of the title. You don't want to see the label, you can get rid of the label. As you can see, this thing kind of goes away. You don't want to see the coordinate system, you can see that. So everything is configurable. You can choose to show loads and constraints. You can choose to show the legend or don't show the legend. So your results window can be customized according to your need, and then you can go save it as a template and reuse it. You also have format legend, where you get to format the legend right here. So you see the max value is 1212. I'm going to change that max value to 1800. And when I hit enter, you should see things should get evenly distributed. The reason they're not evenly getting distributed is because I've had specific values assigned to them. Okay, so if I cancel this out, I'm going to close this and I'm going to create a results window real quick. And now I go format the legend and I go, this needs to be 400. You see how everything here gets changed. Then you can preview, you can see everything above 400 is shown in red. Okay, people use this as another way to define failure criteria. For example, my materials allowable is 600, but the factor of safety makes my allowable for my particular part to be 500. So everything above 500 is not acceptable to me. So what I can do is I can easily do that by just changing the legend value to 500. Once I change that to 500, it's going to evenly distribute those. Okay. Now you can also look at it in different schemes, like say look at the thermal scheme. See that? Grayscale, people who like to print black and whites, you know. You have hue scale. You have a lot of different scale. You know, here's your simulate classic, old Mechanica. So you have these. You can also go ahead and say invert the colors. You see red becomes good and blue becomes bad. I mean, if you want to call that. Okay. You can also have transparent fringes. You see that? It's kind of transparent. It is one way of seeing the 3D. How deep is the surface stress going? So people like to do that. You also have continuous tone. Now, what is continuous tone? You see, I never look at the result with that continuous tone on. The reason I don't do that is because when I don't do that, I clearly see different stress jumps. You see, the stress is flowing more uniformly instead of going from red to blue directly. That would cause a red flag for me that, hey, there's a huge stress jump. If you turn on the continuous tone and preview, you see it kind of blends everything together, kind of gives you a pretty picture. Now, if you're in school and you want to get a higher grade, you probably would do that. When you're at work, you want to turn that off and kind of see if there are any stress jumps. As long as the color flow is uniform according to the legend, you are good over there. So that's formatting the legend values. All right, so let's talk about annotations. The first thing I want to talk about is annotation. So right here, annotation. In the annotation, you can go type in text, say this is passing the test. Okay. Now, you can place it there. Okay. You see, you can mouse a sketch. Okay. You can add a leader. You see how as I move, the leader will stick to it. See that? Now notice this doesn't really stick with the model. Okay, so when you go insert annotation, the mouse over sketch doesn't necessarily stick with the model, but the leader will stick. The node doesn't move, it stays where it is, but the leader will continue to be attached to the point that you picked. Okay, so you see that you can also go do queries, and we'll use a different example, but I'm going to do this one more time where I go annotation, type in anything you want. You can say place the note here, pick a leader, point there, and say OK. Right? That's your annotation. You don't have to worry about like, hey, is this pointing to a right place? It will always point to a location that you picked. Now, there is another thing with respect to annotation. If you go info and go to measures, you can pick different measures that you want to create. If you create a measure that is over here, you can actually show them in your results. So I'm going to use a different example to show this. It will be better with the stress result. So let me open a different analysis. One second. Oh, I haven't created any measures. My bad. I'll show it to you with a different example. Let's move on from here. I'll show you another example with that. Okay. So that was annotations. Next is controlling. So I'm going to open a controlling static results definition file. I'm going to go edit this results window. You see here I can choose to look at deformed shapes. Okay, so you can see that shape is deformed. Now whenever I look at deformed shape, you see that it is an exaggerated displacement or stress because you're scaling it. Okay, you might also want to overlay the transparent undeformed. See that? So that's the undeformed. It's just showing you more or less the direction in which it's going to deform, because the max displacement is 0.18 inches, which you can hardly see with your naked eye. You can also do a transparent overlay. So it kind of does that. So this gives you an idea as to which surface is moving in which particular direction, so that you can map them and look at, okay, this is the direction that's moving. I also like to look at my results with element edges just to see if there are any fractures, breaks, right, or cracks per se. Okay, so you can look at it with your element edges on. I like to do that with the element edges. You can choose to say loads and constraints. I mean, I do that when I'm printing results more than when I'm looking at the results, but you can see the constraints here and the loads right there. And you can also animate. You can control the speed of the animation. You can stop it and go step by step. And this animation can be exported as a video file. Okay. So notice when you are in the animation, certain things are disabled. Okay. When you are not animating, even if you have it stopped, you see these things are disabled. But if I go back to my results definition and don't animate it, now you see I have more things I have available. Okay. Now, you notice here in the info, I have dynamic query. It means I can move my cursor everywhere along the part and you see my query changes. So I'm just looking at a hot part over here and see what the maximum values are. Okay. Now, it still doesn't help me because I'm looking at it like this and I'm just moving my cursor. It's very dynamic. What you can also do in the info is to turn on the location in dynamic query and then go do a dynamic query. It also gives you the XYZ location with respect to the world coordinate system. Okay, so you're looking at a hard point and its location with respect to the world coordinate system, so you actually know a physical location of that area. You also have view max. So you see in the view max, it's telling me that this is where the maximum value is. So I go info view max. If I turn the view to be like that and say info view max, it's going to show somewhere else that that's the max. View max is not very helpful because it only shows the maximum in that particular orientation of your part. Okay, so I don't use it much. So here you can all go ahead and clear all the queries. I'm going to take off the overlay so you can see that better. And here I have model max. So regardless of the orientation, it's only going to point the maximum area or the stress value in my model. Okay, it's giving you the XYZ location and the max. You can also get model minimum. What this measure gives you is if you run the analysis right here, see this is what I was trying to show you. What it gives you here is I can show, hey, show me where the displacement is maximum and create an annotation for me. So do you see that? Kind of creates the annotation. You can also say, show me where my von Mises stress is maximum and create an annotation for me. So that's where my von Mises stress is maximum. So that was what the measures that I was trying to show you was. I think I had animate on, so I couldn't get to this window. It wouldn't show any results. But as you could see, all these are inbuilt system results that you can point out. Instead of you having to dynamically measure and make a note of it, you can easily go ahead and look at, and create that annotation very easily. Now you can also go, like I said, just clear. Okay. All right. So that was our annotations and controlling the animation part of it. Okay. Now there's a few more examples. I mean, like I said, I got a bunch. Let's go over all of them. So I'm going to insert a results window. I'm going to open. So you notice that I don't have anything saved. That's why I don't see an RWD file. If that's the case, then you would insert. Open that part. So you see this is stress. And now here, I'm going to show you deform. Okay, so here's your stress and that's the deformed value, and that's fine. So if you go back to your edit results definition window, you can say continuous tone on over here, and you can see it's showing you the same thing. Like, it's just nice and smooth. You don't see any stress jumps. So it's good for reports. Now, what I also want to show you is I want to turn that off, and I want to show you the contour. So here I'm going to check the contour. What does it give me? It gives me the 3D curve representation of how deep my stresses are. So you can see it's like a wire diagram kind of thing. Just curves. Now that doesn't really help me as much as creating ISO surfaces. So this is good because it tells me how deep that stress value is going. It kind of goes deep, and it kind of like it's like an onion, skin. You can peel off layers and look into it. So that's like a 3D flow of stress inside your part. This is very important because what we are generally looking at is the garbage that we look from the top, which is, hey, I made some colorful pictures. These are my, this is what I got. But you're looking at it only from the top. Okay. Now, doing the ISO surfaces and contour, you can actually see the depth of the stress or depth of displacement of any measure that you want. All right. I'm also going to go here and say cutting capping surfaces. Okay. So when I click on that cutting and capping, I have two options right here. I have a cutting surface and a capping surface. If I do a cutting surface, you see it's defined with respect to a world coordinate system. You can also use a 3D 3 points. You can use the user-defined coordinate system. You can use a screen point. You can use ISO surfaces. So different options here. Now you see the XY plane, so you can see the XY right here. And I'm going to hit apply. It's only going to show a plane at 50% depth in the XY direction. I can say dynamic and then left mouse button click, and you see it's going to move in opposite direction, guys. You see my mouse is going up, it's moving in the opposite direction. So I can cut across and really see what's happening inside this part. Now if I middle click, I get this back. I can go YZ direction or XZ direction, which is this plane, apply and dynamic, and then drag it through this way. If you want to get out of it, then middle click. Instead of cutting, if I say capping and I pick an XY plane, apply, you notice when I click on dynamic and I left mouse button, keep it pressed and drag, you see it's actually filling the part as it goes. So here you get to see how deep the stresses are going at different locations along the part. So you can see the depth of the stress. Now you can say OK and leave it like this, or you can say cancel, it will come back to the full-blown model. So if I say OK, so that's what I get. Now, what you can also do is this is your results window. Here you want to insert a new one. So I can go insert a new results window. I can pick an entirely different model. Let's just pick this part and say OK. So you can see them side by side. Right? Now, as you move along, you see that here you can choose to remove that and say OK, only one window is shown. You can go here and choose to show both, or remove one and show only one. You can go here, pick both and show both. Now when I click on it, that becomes green. When I click on this, this window becomes green. You can see the red and green right here. So I'm going to click here and I'm going to delete it. Now when I go show, I only have one window. See, this kind of goes show and hide basically. So you see, I can hide it. I can go back to show, select that and say OK, it shows up. So that's your show hide. Now if I want to create another results window of the exact same model or the same analysis, I can just hit copy and say, hey, I'm looking at stress there, I want to look at displacement. So here I'm looking at stress and displacement of the parts side by side. Now you can choose to delete them. That's the difference between copying an existing results window and changing the quantity, format, whatever you want, or inserting a brand new results window where you can compare two parts side by side. Now why would you do that? Now let's say I'm working on a design, you worked on a different design, I want to compare the results of both these different designs side by side, I can choose to do that. Alright. Moving on, you also have graphs. So let me set my graphs on my working directory. I'm going to open my results window and see if there is a graph. Right click. Alright, there's nothing in there, so I have to create it. So insert a new results definition window. Okay. You notice I'm going to ROD LS, which is the local sensitivity study. As you know, that the result of a local sensitivity study is only a graph. In a sensitivity study, you basically change a dimension or a parameter and see how your measures are getting affected. So the parameter that I'm going to change here is the rod neck. Okay, that's the design variable. So I'm going to go pick a measure. So let's see, how does my maximum displacement change with that? So as you see, you can, as you increase or decrease your neck dimension, your displacement changes in here. Okay, so you get graphs like this. Now, what you can also do is you can format the graph. So if I go here, you see this is my y-axis. You can change the label. You can choose to display it or not display it. You can see right here this label. That's the quantity and that's the name. You can say displacement and hit apply and it shows up right there. Okay. You can also go mess with this text style. Right? You can change its font, you can change its height, you can change all of those within the text style. You see that's the maximum value, that's the minimum value. You can go ahead and change the max and the minimum values. You see the major marks are 6 of them. You can go change that major mark. You can also add minor marks under there. Okay. You see the line style, you can say solid. You see that? You can say dashed, or you can say none. Okay. You can change its color. See, you have a little RGB. So I don't know if there are any K-State guys, making them happy, making it purple. You can change the thickness. You see that? You can change the scale to go to a log scale or a regular scale. You see the tick labels are horizontal or vertical. You can choose that, and even they have a text style. Even here in the x-axis, right there, you get all the same type of definitions that you can mess with. Data series, you can see the points are shown in blue. You can choose to show them in yellow. The line is shown in blue. You can choose to show them in green. Point display is a circle. You can show triangle. You can show smooth curve instead of linear curves. You can change the thickness of it. You see the graph display at the very top. Here it's going to show you some information. You can edit those. You can blend the background right here, and you can go change that. Say the top is more like that. So all these, you can see the triangle right here. See how the points are shown as triangles. So all these can be changed, and it can be saved as a graph preference file. Okay. So when you save this graph preference file, you can point your config.pro to use it. So every time you create a graph, you get this particular formatting that you want. Okay. So that's with respect to graphs. All right. We went through queries, we went through fringe. So let me show you some more examples, and then we'll get into another concept right here. So fringe plot. Okay. Let's see. Okay, this doesn't have it, so we gotta create one. So there is your rod results. You see, you're looking at stress. What I like is the display option. So I can say it's going to show everything. I can pick certain curves, certain surfaces, certain volumes. If you're running an analysis for an assembly, you can pick certain components and hide them so you can look at the result better. So here I'm going to say surfaces. Click over here, and I can pick. Say I'm more interested in those. So you get to see the results of that. Okay. So again, it's giving you surface stress. It's not giving you the 3D, but kind of shows you those surfaces only if you want to look at that. Okay. So you can filter out. So how do you go? Edit, display location. You can just say all, and okay, it's going to show everything. All right. Now we spoke about format, info, inserting, viewing, edit, and file. Now you see you can go export this to Creo View. If you guys have Creo View, you can export it to that. You can export this to image, so you get JPEGs. You can export this as an HTML report, so it's going to create a little folder with a web page where you can look at these results inside a web page. So people who like to post them on their websites, they can do that. Direct VRML is it's going to take this solid deformed part and export it as a VRML file, which you can re-import it back in Pro-E and kind of like place one on top of the other to see what the deformation is. So you can get all those. If you have animation on, so if I go turn on the animation, I also get to export this as a movie. Okay, so I get these exports. Now what I'm going to try and show you is tying the results. Okay, so let's look at tying the results. ones. Okay, so I'm going to pick this. That's the first modal analysis result, mode 1. I'm going to look at stress and say okay. So it gives me this. Now I'm going to copy this. I'm going to change it from first to the second, so I can see things side by side. Now you see the red over here doesn't match with the red over here because the legend values are different. Okay, see that? The legend values are different. So you can go utilities, tie the legend and pick. So you see both of them now 12, 12, 12, 12 have the same legend value. I can also go untie it. Now I can select this and say tie the legend with this. So you see this becomes the maximum value of that and you get different results. So because your results window, the colors depend on the legend, making sure the legend is correct is the most important thing in your results or post-processing. Alright, so now that we went through all these buttons and all these menus, I want to talk to you guys about how do you approach an FEA problem, okay? How do you go about working on it? So here I'm going to open a bracket part. As you can see, I have a bunch of analysis done right here. So this is my little bracket, okay? Applications simulate right here. You see that I have a constraint where I'm fixing that and I'm putting some kind of a load over here. Right? Simple analysis. I've run a bunch of analysis and I'll go through each one of them with you guys. So first thing I ran is a quick check. Okay, you notice in a quick check it runs one pass where all your polynomial orders, the element edge polynomial orders, are at order number 3. Okay, the max it could go to is 9. Okay, so everything is at 3. It gives me a result. I can actually look at the result and say, hey, you know what, is it deforming the way I wanted it to? Okay, that's how it's supposed to be. Is it accurate? Definitely not, right? But this is before I run a complicated analysis. I want to make sure that I'm setting up the analysis right. So I run that. If you look at the summary file right here of that quick check, it just gives you values. Notice there is only one pass right here. See that? Just one pass. No convergence, just one pass. Okay. Now once that's done, I go run a single pass. Okay. In a single pass, when you click on the summary file, you notice that you get a couple of things. So here, it's going to create the mesh for you. The first pass, in a single pass, all the element edges are at edge order number 3. Okay. That means the element edges are defined with a cubic curve, so that it can map the element or the geometric boundary exactly. Then based on the local stress errors, that means the value of, say for example, a stress value on one edge is compared to the stress value on the adjacent edge, and if the difference is large, the edge orders gets bumped up to map the shaping function. So here you see that here the maximum edge order is 5. And it kind of tells you the error in the principal stress. So you see that 11%, anything more than 5%, I wouldn't put my money on. Okay, so that's how you look. That's the first thing you look. You look at 3, you look at 5. Okay, it could have gone to 9, but it didn't go to 9. Okay, here you see the percentage of result. It says like, okay, 11%, right? I mean, it's more than 5. 5 is a good cutoff point. And you also see, you get all these results right here. So obviously you know that if it's converging up to 11%, then something's not right. Now, is your analysis not set up right? No, your analysis is set up right. Your boundary conditions are correct. Your loads are correct. But your results, you cannot, trust your results yet because the convergence is at 11%, or you can say the error is 11%. Okay. Now I run a multipass. So if I run a multipass right here, you see I'm going to change this from a single pass to a multipass. You see the maximum polynomial order is 1 to 9 and the percentage of convergence is 5, and I'm choosing the default, right? It's going to converge on local displacement, local strain energy, and global root mean square stress. Now, when I run that and I look at the summary, so I go back here. So notice there is pass 1. Everything is at 1. Okay? Even a curved element edge is defined with a first order equation. Okay? In the second pass, everything gets bumped to edge order number 2. That means the curve is defined with a second order or a quadratic equation, like on a second order quadratic equation. Okay. Now from order number 3 onwards, it could go up to 3 or 4 or whatever, right? It keeps bumping. So what is the reason for this bump? So what it does is, let's say we take this edge. In the first pass, this was at edge order 1, so it was a straight line. It finds out the local displacement and the RMS stress. In second pass, it's going to bump this up to edge order 2. It's going to find out the local displacement and RMS stress. It's going to compare the values between pass 1 and pass 2 for the exact same edge. Is this within 5%? Because we said the percentage of convergence is 5%. If it's not, then it's going to bump it up to 3. Okay. Now, what it's showing right here is the maximum edge order. Doesn't mean everything is at 3 or 4. Some of them are at 3, some of them are at 2, some of them are at 4. It just shows the max edge order. So if the difference is huge, instead of going to 3, it will go directly to 4. Now another thing you also have to notice in this results window is at the bottom here, you see number of elements not converged and number of edges not converged. You need to make sure that these are zeros. Okay, so you keep going. You notice the next pass, it goes up to number 6. Okay, it still says that the number of elements who did not converge within those 5% for our measures and number of edges that did not converge. So notice it's going to 6. It's running another pass at 6 where it bumped up the other edge orders to 6. Number of elements not converged, number of edges not converged. Notice at 6, it's going to tell me that these are the number of elements and edges not converged. So as of now, I'm good, right? It's 0. Now, next thing you want to look at is the maximum principal stress is 3.4% error, okay? You also see right here, you have that value to be 414, okay? Because it's 4.14 e power 2. So that's kind of like out of our range. Next, you also scroll down and you look at all your quantities, okay? You see that Z displacement is not converging within 5%, okay? Maximum stress YY and YZ are very close to 5 or more than 5, okay? So now, what I need to do now is I cannot trust this result because it did not, all the quantities did not converge within 5%. What I end up doing is I go run a multipass again, but this time, instead of converging on the local displacement and strain energy, I'm going to pick my measures. You see measure, and I'm going to pick your maximum stress YY and maximum stress YG and say converge on these. Okay. So now I'm going to look at the results for that. So when you look at the results for that, you could directly see here some of the results were like crazy. You see that? None of these others are getting converged within those percentage except those two. Those two are within 5, but you see you have a whole lot that is kind of out of sync. Here, Again, I am not worried about stress values yet. I'm just looking at the percentages. Then I'm going to look at a result. In the result, I'm going to look at P level. Okay, P level. So it's going to show me that, hey, the P levels on these element edges are at 6. You can see there's a green line that says P equal to 6. So you can see that your element edges are huge. So you might want to refine the mesh. So you can use your mesh refining techniques, create a smaller mesh, and then you run another analysis. So here I'm going to run another multipass, and here you notice that I have picked all the results that did not converge. Okay, and I'm forcing them to converge too. And now I look at my results right here. You can see how many passes. Pass 1, pass 2, see pass 4, pass 5, pass 6, pass 7, it goes up to 7 now. Pass 8, it goes up to 8. It also goes up to 9. See, whenever it hits 9, I'm a little skeptical because who knows if number 10 was available? It could have gone to 10, right? So I get a little skeptical, but I also look at my elements converge to be 0, so I'm happy that everything got converged. You see the stress error is low right here. You have to now go back and look at all your percentages. So you see that you still have these two right here. Maximum stress YZ, maximum stress YZ and XZ. Both of them are not converging. Okay, so I run another analysis which will force them in, and here you can see all the percentages right here are converged. So you keep force converging. Once these are converged is when I really care about these. If these don't converge, don't even bother looking over here. So things that need to happen for us. Number of passes. You look at the maximum edge order and you make sure that number of element edges and elements are converged. Okay. Then you also look at the percentages of convergence throughout here and make sure that everything's within the 5%. Once that happens, then you can trust your result because you can look at your graph. You see, I'm going to look at a graph. I go here and say graph, and I care about my measure. I want to see how did my 1 Mises stress converge. Right? You want this to pretty much be a straight line if possible. Okay? So then you can say that, hey, look how my results are converged to where they cannot be improved any longer. So if I go here and say, where's my 1 Mises stress? Let's add more passes. So you can see it runs all these passes to make sure that that's a straight line. Hey, you know what? It cannot be improved and it's kind of approaching a straight line. Now you can trust the quality of your result more than anything else. So when you look at results, like I said, you know, setting up the analysis and producing colorful pictures is one thing. How do you read a results summary file is the most important thing. How do you make sense that, hey, is it okay? Is it good? Do I trust it? How do I make sure that I trust it? How do I prove to other people that these results are good? So these are things that you would need to prove that your results are good. All right, so that's what I had in terms of demo. I'll leave it open for any questions. Jason, do you see any questions, buddy?
Yeah, let me get a couple questions here. Just a couple. Can you query stress using cutting and capping surfaces?
Can you query stress in cutting and capping surfaces, correct?
Yes.
Okay, give me a second. Okay, cutting and capping. So here it is. All right, So let's do a cutting surface or a capping surface real quick. Okay. Now, info, dynamic query. See that? Is that fair? Okay, what's the next question, buddy?
All right, let's just do one more, then we can wrap it up. Can you show a simple way to do a linearized stress query?
Linearized stress query.
Yes.
I need a little, okay. 1 second. I need to have a result window that is compatible with that. So let me close this and create one real quick. You have to, don't know if I have a results window for that. So model stress linearized stress query. There you go. Oh, it went away. So here I'm going to do it one more time. Linearized stress query, you pick one. Cite the model or the element boundary. Okay. Can you see that line right there? I don't know if you can see it.
All right.
So that's how you do that linearized stress query.
All right, then do you recommend Simulate for large weldments, or is it only suitable for parts?
Large weldments. When you say weldments, you're talking about like huge frames being welded together in an assembly? Yes. You wanna give me just a second. Just give me a second. I wanna show this to you. In that way, you have a lot of people use Simulate for welding. Okay, and I personally use a lot of Simulate for welding. Just give me a second. I have an example that can show you how stress kind of like works within Simulate, and how you can use what do you call it? How you can use traveling heat loads to simulate the welding process, and how it kind of heats up the rest of the model, and what kind of thermal stresses are induced. So you can simulate your entire welding process as if your weld gun is kind of moving along the weld, and analyze that. You can also use Pro Weld feature to create welds in there, and all those welds would be treated as welds inside of Simulate. And within Simulate, when you do assemblies, you have a lot of model setup options, like say, are two plates, for example, are they in contact? Are they bonded? That means as if they are fused together. Are they free? That means they can move with respect to each other. So a lot of my customers, at least in the ag industry over here, they use Simulate to analyze their huge frames for tractors, or like loaders and stuff with Simulate, if that's the question.
Very good. We're going to go ahead and do a couple poll questions, and any questions that anybody put in we'll get back to after with a follow-up. The first poll question: what version of Creo are you currently using? And thank everybody for the responses. Question number 2, which Simulate do you use? And then one final question. What other topics would you be interested in over the next couple of months regarding Simulate? And thank you everybody for the responses. Anybody can go back and watch this webcast by going to our homepage, www.bwir.com, or on our YouTube page. And if you ever have any questions, please reach out to me, and I can forward them along to Sukumar, and he'll get them answered for you. And you can also reach out to Jim Webb, our TJ, our Vice President of Partners. Thank you, everybody, for attending today's webcast. Please let us know if you have any questions.